The notes are on percent error, and this is target 1.13. So first, what is percent error? Well, percent error is going to show the difference between an experimental value compared to the real or known value as a percentage. So experimental values, these are going to be what you get in your data that you take during a lab or experiment. That's why it's called experimental. And this is going to be compared to the real or the known value. And this is going to be given to you, or maybe it's a piece of previous knowledge you might have, like the freezing point of water is 0 degrees Celsius. And this is sometimes called the theoretical. And why we need percent error is because numbers in lab experiments can be very misleading because it depends on the magnitude of what you are measuring. For example, if you measure the circumference of the Earth and you're off by 1,000 miles, that's only a 4% error. That's pretty good. If you measure the length of a paperclip and you're off by only 0.5 centimeters, that's a 13% error because that paperclip is not very big. So we want to know how wrong we are based on what we are measuring. So our equation is that percent error is the theoretical minus experimental, and that's going to be in absolute value bars, divided by the theoretical. And what's missing is a little times 100 so that we can make it a percent at the end. Now, absolute value bars means that if your number is negative, you make it positive. And theoretical, remember, this number is going to be given to you in most cases, maybe just written in the problem. Maybe if you're doing a lab, it's going to be given to you in a data table that I provide. And the experimental, this is the number that you get in the lab. And because the top number is in absolute value bars, it doesn't matter the order. So you could think of it as experimental minus theoretical because you're going to make it positive even if it's a negative number. So the order doesn't matter. But what is important is that is the theoretical number on the bottom. That is important. So what kind of number are we going for? Because percent error is how wrong you are, how much error you had, we want a small percent error. So we're going for something less than 10%. That would be good, right? That's 90% right. That would be an A. We like that. So let's take a look at an example. Joe and Susan are performing an experiment in the lab to test the density of aluminum. From their data, they determined the density to be 2.65 grams per milliliter. I'm going to underline that because I see a number. I'm probably going to use that later. They checked the table on the lab and they found the actual density is 2.7 grams per milliliter. So what is their percent error? So as I read this, it says from their data. So this is a number that they got in the lab. So this number is my experimental. And they checked the actual density or the known density, and they found that the theoretical is 2.70. So now that I have my numbers labeled, I'm ready to plug it into the equation. And percent error is the theoretical 2.70 minus the experimental 2.65. I'm going to put that in absolute value bars, divided by the theoretical 2.70 times 100 to make it a percent. So when I take 2.70 minus 2.65, I get 0.05. And because that was already positive, I don't have to worry about the absolute value part. And I divide that by 2.70. Now here's where you can see it doesn't really matter the order of the top, because if I would have set up the equation like this, then I would have got negative 0.05. But when I take the absolute value of that, I end up right there again. So the top, The order doesn't matter as long as you remember the absolute value bars. So no matter how you set it up, we end up with 0.05 divided by 2.70 and times 100 is going to give us a percent error of 1.85%. I like to just round to 2 decimal places here. I think that's what makes the most sense. So good job, Joe and Susan. That's definitely less than 10%. Let's try another example. Sam and Bob are performing an experiment to test the boiling point of water. They found the boiling point to be 98.4 degrees Celsius. Notice they found. So since they found, this is what they found in the lab, this number is my experimental. What was their percent error? This problem doesn't give me my theoretical. Does anybody know what the theoretical value is here? The boiling point of water is 100 degrees Celsius. You thought 212 degrees, that's in Fahrenheit. So we have both our numbers now. Let's plug them into the percent error equation. I'm going to take my theoretical 100 minus my experimental 98.4, take the absolute value of that, divide by 100, my theoretical, times 100, and then a little bit of math. So 100 minus 98.4, 1.6 was already positive, so don't have to worry about the absolute value bars. Divided by 100 times 100. Here, my 100s end up canceling. I don't even need a calculator to find out that Sam and Bob got a 1.6% error. Now, on the last one, I rounded to 2 decimal places. Here, 1 decimal place makes sense. For example 3, I think this would be a good time for you to pause the video and give it a try yourself. All right, now that you tried it yourself, let's see how you did. You and your lab partner are trying to determine the mass of a solid that's remaining after a reaction. This is called the precipitate. We'll do a lot of this in second semester. You record the mass to be 0.33 grams. The known value is 0.45 grams. What is your percent error? So because I recorded this is the experimental, and the known value, that's the theoretical. So now that I have them labeled, I can go ahead, plug them into the equation. So the theoretical, 0.45 minus the experimental, 0.33, absolute value, divided by theoretical, times 100. And 0.45 minus 0.33 is 0.12. Already positive, so don't have to worry about the absolute value. Divided by 0.45 times 100, and oof, you and your lab partner got a 26.7% error here. Not as good. But if you got 26.7, you did your percent error equation correct. And that's the end of our notes today.